right, thank you so much, everyone. Happy Friday. Thank you for coming to the lecture. And I'll be introducing our speaker today, Kai. So Kai grew up in Maine and graduated from Amherst College with a double major in physics and math. In his undergraduate thesis, he conducted experimental research on molecular nanomagnets, which have potential applications as qubits in a quantum computer. At Berkeley, he continued working as an experimentalist in Hartmut-Hafner's ion tracking group before deciding to become a theorist. Since 2022, he has been working with Brigitte Wally on problems at the intersection of quantum mechanics and gravity, and he will give us an amazing talk today.
Thank you. So I'm Kai. I'm a seventh year grad student in physics, so don't tell anyone. I work with Brigitte Whaley. I'm a theorist, but I have an experimental background, and I'm interested in experiments that can test something about gravity. So in this case, it would be a particularly good test of classical gravity, so classical general relativity. But I'm also interested in testing whether gravity is quantum mechanical, and basically anything we can measure about gravity using quantum systems is what I'm interested in. I guess in the invitation, it asked me to talk about how I got here. So I'll just say it very quickly. As you said, I was an experimentalist in undergrad, and I started grad school as an experimentalist. But I always kind of really wanted to be a theorist, and it was just sort of an insurmountable challenge because I had no background. And so, becoming a theorist in halfway through grad school and finally getting to this point was major challenge. So if anyone else is thinking about what they're interested in, what kind of physics research they want to do, or anything, I'm happy to talk about that more. So I'll start with the talk. So I'm going to be talking about how to measure gravitational frame dragging on Earth with superfluid interferometer. So I'm going to start by, is this working? Well, I guess I can just use this. That's not working either. Oh, now it's working. Wait, slide. Okay, finally, that's the slide I want. I don't know what's happening. All right, so here are the main characters of the talk. On the one hand, gravity in the form of Einstein's general relativity, and on the other hand, superfluid helium. Do we even close the shades to get a little bit better? Guys, in fact. Okay. So we have Einstein's gravity, and we have, on the other hand, superfluid helium. So I'm just going to quickly introduce you to these two characters. General relativity is Einstein's theory that describes gravity as not a force between two objects, but a curvature of spacetime. And there's this famous quote from John Archibald Wheeler you might have heard: "Spacetime tells matter how to move, matter tells spacetime how to curve." So this is describing the fact that you have some matter like the Earth. It is creating a curved geometry of spacetime itself, and that curved geometry is determining the dynamics of objects near the Earth. They're moving on that curved spacetime. Is this sort of a familiar concept? Okay. And one particular prediction of general relativity, which is one of the less famous ones, is that this thing called frame dragging. So general relativity predicts that if you have an inertial reference frame, for instance, near the Earth, the axis of that frame will be rotating slightly relative to distant stars due to this effect called frame dragging. So what does that mean in practice? Think about having a gyroscope. So a gyroscope could be something like, imagine a spinning top. Like you have a little toy, like a top. You spin it. It has some axis that it's spinning about. That's basically the picture you'd have for a gyroscope. The reason it's a gyroscope is because if it is rotating, if it's in a rotating frame, the axis that it's rotating about will change slightly. It'll move, so that the top will not be. You've probably seen this if you played with the top. It will be spinning, but it will also be sort of tilting and gradually precessing like this, right? So a gyroscope or a spinning top near the Earth will very, very, very slightly precess just from the fact that the Earth is spinning. The Earth's kind of dragging it with it. And there's this nice, can I click on this link and get a video? There's this really nice website. It has these two animations. So here's first what happens in Newtonian gravity. You have the Earth spinning. Space-time is this flat surface. You have some gyroscope, which is spinning outside the Earth. It's attracted to the Earth, but it's just spinning in a particular direction. It's not changing the direction of its rotation at all. So this is Newtonian gravity. And then we go back. Now we click on the general relativity picture. This is Einstein's theory of gravity. Now the Earth is warping space-time. It's no longer flat. And now I think the Earth's going to start spinning in a minute. Yeah, so you have this sort of curvature space-time. Yeah, now the Earth is spinning, and this is causing space-time to warp in a new way. And of course, this is sort of just a intuitive image. It's not really something quantitative, but now you have the video is glitching a little bit. But you have this gyroscope, and it's orbiting the Earth, and now it's not keeping constant direction. You can see the yellow arrow is the axis of the gyroscope, and the white arrow is where it would have been if space-time were flat. So you can see, let's play the end again. You can see that as it orbits the spinning Earth, the Earth drags the gyroscope axis with it a little bit. So this is the effect we want to measure. All right, and now go back. Yeah, now we're back here. All right, and now we have the second character, which is superfluid helium. So superfluidity is a property that was discovered in 1937 by Kpizak and Allen and Wiesner. And what it is when you have, say, a bucket of helium and you cool it below a critical temperature, which is 2.17 Kelvin, the helium condenses into a superfluid state. And in that state, it has a number of special properties. Most notably, it can flow with no viscosity. And another interesting property that would be important to us is that this whole macroscopic amount of helium can be described by a single quantum wave function. So normally, if you've taken a quantum mechanics class, you might be used to describing the wave function of an atom or like a single particle. Cool thing here, you have a macroscopic bucket of superfluid helium. It's described by this very simple wave function. They're all in a quantum state. It's in a single quantum state, all of these. And there's like 10 to the 24 atoms here, all doing something quantum together. It's amazing. We have another fun video. This is not really important for the talk, but it's fun. Superfluid helium is so fun that I want to play this. Is it gonna play?
In the lambda point, the superfluid component of liquid helium creeps up along the walls of its container in an extremely thin film. It is known as the Raman film. This creeping film is a variety of superflow. It is difficult to make the film itself directly visible to you. To show it indirectly, we've put some liquid helium into a glass vessel. It is below the lambda point. There is no porous bottom in this vessel. The film rises along the inside wall and comes down along the outside, collecting in drops at the bottom. The thickness of this creeping film is only a small fraction of 1 micron and of the order of 200 to 300 angstroms. Its speed, while small just below the lambda point, may reach a value as high as 35 centimeters per second at lower temperatures. Our next experiment deals with the phenomenon of second sound.
So there's a whole series of really cool videos about superfluid helium, various different properties it has. So that was, I think, just one example that I wanted to play to get you excited about superfluid helium. All right, so those are the characters. Now what are we going to do with them? So here's where we're going to start getting a little bit of math, and hopefully I won't lose anyone. I'll try to explain just like qualitatively what is happening in each slide. So I said earlier, this frame dragging refers to the fact that inertial reference frames near a rotating mass will precess. They will rotate slightly relative to frames at infinitely far away, like a distant star. That's infinity. There's another effect called geodetic precession that's very similar, except you actually don't even need the Earth to be rotating. You just need a static mass. So these will both be present on superfluid helium. And the motivation for why you would want to measure this is, well, it's just a really cool thing, but also there are there's this class of theories called general metric theories of gravity, which describe basically variations from general relativity. So you can change general relativity slightly and still have a theory of gravity that looks like it describes our world. And if you want to test whether general relativity is right or some other metric theory of gravity is right, you need to measure a set of parameters called post-Newtonian parameters. And this experiment would test two particular parameters called gamma and alpha 1. So this basically, the motivation for this experiment is testing general relativity as opposed to against like other theories of gravity. Okay, this is the most important equation here. What it means, S, is that arrow sticking out of the top of the spinning top. That's the thing that's changing. So this is saying the time variation of that vector is given by the cross product of these. These are the precession rates, they're angular velocities. So you take this cross product of angular velocity with the vector itself, and this is the time variation of that arrow sticking out of the top of the gyroscope. And here I've just written, you don't need to understand these at all or what the symbols mean, but these are just expressions for these angular velocities. You can see they involve these parameters gamma and alpha 1 that you would want to measure. And this one is related to how fast the Earth is rotating. This one is the geodetic effect, which is not related to how fast the Earth is rotating. All right. So we want to measure these omegas. That's what we want to measure.
Oh, sorry, I have a question.
Yeah.
So you're making some assumption about what kind of post-Newtonian parameters were that formula that you're using, right? Otherwise, so that's how you can propagate those into these two equations, right?
So the way you do this is you write down the metric of a rotating sphere in this post-Newtonian framework and with all the parameters in it. And it turns out if you calculate these precession rates, these are the only two that matter.
So yeah, so my question is, Y, you have alpha in front dragging frequency
Uh-huh.
and you also gamma. Only gamma for geodesic frequencies. That's based on some specific type of post-Newtonian force, right?
This is, I think, within this so-called post-Newtonian framework, this is, I mean, there are, so these two parameters have physical interpretations. I think, for example, alpha one is something like, if um, if there's like an overall velocity of the frame, an overall velocity of the frame of the universe or something like that. But I
Oh, wait, I think I'm confused. Okay, so it's post-Newtonian.
Yeah.
So you're still in classical gravity.
This is still classical, yes.
Okay, got
Yes.
it. I was thinking, this Yukawa, we had the strength of alpha and.
Oh, no. This is
like,
completely
quantum gravity
classical,
thing.
yeah.
So, oh, sorry.
Yeah. Next question. Yeah, so these things are what we want to measure. So here's just a quick summary of previous measurements of this vector. Yeah.
What's the physical intuition for gamma then?
Oh gosh, I think gamma is how much it's related to like how much curvature is caused by a unit amount of mass, I think. When we think about this, so yeah, gamma in general relativity is 1. So like 1 unit of mass causes 1 unit of curvature, and then this is parameterizing like how far away from that you are. I'll double check again. I think that's what it is. Alpha 1 is 0 in general relativity, so it's saying there's like no preferred frame, and so if it's non-zero, that means like there is a preferred frame. So these are previous experiments that have measured this. There was this satellite in the 2000s called Gravity Probe B. It was a really cool experiment. They put these literally like that image, that video I showed you at the beginning of these spinning spheres orbiting the Earth. That was from the Gravity Probe B project, and they literally had silica spheres that were like the most perfectly spherical objects ever made, like to within 1 atom or something width. They put 4 of them on this satellite, and they literally looked at that arrow that I showed you in the video, that angular momentum of the rotating silica sphere. They saw how it changed over time, and over the course of like a year or two, they were able to see that it changed relative to the distant stars. So that's a really cool experiment. It's also a really difficult experiment. So they were only able to measure the effect to a 20%, the 20% level. So they were able to say general relativity is right up to like plus or minus 20%. There's other experiments where they just track the orbits of satellites. Those claim to have gotten 2%. They're a little bit controversial because the analysis is extremely complicated. But they claim to have gotten 2%. This has never been measured on the Earth. These are all satellite experiments. One proposal to do that is something called ring-laser gyroscopes, which I won't talk about. But then what I am talking about is our proposal, this with a superfluid gyrometer. And our claim is that you could do an order of magnitude better than the previous best measurement. Yeah?
To be clear, the geodetic and I forget what the other term is, but the angular momentum one scales with over r squared, one with over r cubed.
When
So
there you go.
yeah, I guess
It's a little bit hard to tell from here because
is there a hidden r inside the
let's see. I think they're actually good. Yeah, they're both r. Oh yeah, this is r squared. Yeah, I guess they do have different scaling unless I'm missing something. Yeah. Yeah. We've thought about, well, I'll come back to this step later if I can. Yeah, so this is our idea to measure this an order of magnitude better. So okay, now back to the second character, the superfluid helium. So you can make so that I said before it's described by this macroscopic wave function. This rho s is the density of the helium atoms, and this phi is a quantum mechanical phase, the phase of the wave function. And you can build something called a Josephson junction. If any of you know what an electronic squid is, yeah, this is just like a Josephson junction in electronic squid, but instead of for electrons, it's now for helium atoms. And Josephson junction is what it actually looks like for helium is you have these little tiny, you have a membrane and you have some tiny pores of the order of microns. And this provides a weak coupling between the helium on one side and the other side. And then the flow across this junction obeys these equations. And these equations are a little weird. They look very innocent. But what this is saying is if you apply, so normally if you've taken like a class on like a circuits and you have a constant voltage across a resistor, there'll be a constant current, right? If you have a constant pressure difference, which is the equivalent of voltage, the phase, this phase of the wave function will vary in time across the junction, and that will lead to the current to vary sinusoidally in time. So you apply a constant pressure difference and you get a current which is oscillating across the junction. It's really weird. Yeah, that's what I'm saying here. You get this oscillating current. Superfluids are just wacky. So how can you use this? You build, so you said you know what a squid is. This is a superfluid version of a squid. For people who don't know what a squid is, you have a ring of this blue stuff is superfluid helium. And then you have this Josephson junction, which is the thing I just showed you. And then you have a diaphragm, which is basically like a kind of springy surface that you can like drive it. You can apply some force to it. And when you apply the force, it pushes the helium and it drives the current around. And this acts as a so-called hydrodynamic circuit. So you can draw the equivalent circuit diagram. If this were an electrical circuit, this would be the circuit diagram. So it has some resistances, it has a capacitance, has an inductance, and it has a weird thing, which is a phase-dependent inductance. In electrical circuit, this would be saying that this is a nonlinear inductor. It's a voltage-dependent inductor. You have a question? Yeah?
Yeah, so you're saying you're driving pressure differentials by a diaphragm?
Yeah.
So, okay, I want to understand this because when I think about superfluid helium, I think about the fact that it is a single quantum mechanical wave function. So it has no viscosity. So the moment that I drive a pressure, it should just immediately rearrange, right? Because to me, I'm confused why pressure is the generator of quantum mechanical phase here. Because like when I think about this with a squid, it's the magnetic flux across, right? And in here it feels a little bit like the analogy would be that it would be the current trough.
So the analog of magnetic field here is not the pressure. The analog magnetic field here is actually the rotation flux.
Okay.
We'll come to that in a minute. But you can think of this pressure drive basically like a voltage drive in a squid, I think. Okay. You look dubious?
Yeah, we use this.
Okay.
We kind of know what it's. But that's a good question.
Okay, and then the other thing is when you're driving with the diaphragm, how do you know that it's generating a pressure, like a pressure differential, and it's not just scattering a ton of quasi-particles into your system? Because like this is something I worked a lot on, and I'm kind of curious. It may also be that you guys haven't thought about like
so I have to say, caveat, I'm not an experimentalist. I know from my colleague who's an experimentalist that you can build a junction that that does just give you this drive that you want. We will be considering the noise introduced from this junction though. From this diaphragm. That will be important. Yeah. Thanks for the questions. Yeah, so this phase-dependent inductance is coming from this Josephson junction. You can think of it as a nonlinear inductor. And then so what we want to measure is ultimately the rotation rate, the rate at which this thing is rotating. And what I'm going to show down here is that that is related, that can be measured by measuring the phase across this junction. So because this is all described by one big coherent wave function, you can if you integrate the change in phase around the loop, the change in so the wave function has this phase, but it doesn't have to be globally the same everywhere. It can vary in space. So if you look at how it changes in space and you integrate that change over the loop, the total thing has to be, well, 0 or more generally a multiple of 2 pi in order for the wave function to be well defined. And well, there's one step that I forgot to write here, I guess, but this gradient of the phase, you can show that it's related to the velocity of the fluid. So this Vs is the velocity of the superfluid in the tube. So when you integrate the phase around, you're really integrating the velocity around the loop. And so what you're saying is the integral of this velocity plus whatever discrete phase you get across the junction, that sum has to be 0. And therefore, rearranging this phase across the junction has to be minus the integral velocity. The velocity, if this is rotating at some velocity omega plus, I'm using this omega plus because that means the velocity of the Earth. So let's say it's rotating with the Earth. The velocity is omega plus cross r, where r is the position. And then you use Stokes' theorem, and you get at the end that the phase across the junction is equal to basically the dot product of the angular velocity with the area of the loop. Sorry, this should also be O plus. Should I say O plus? Yeah, so this is how the phase across the junction depends on the angular velocity of the whole thing, the whole loop. So now we've reduced the problem to measuring this phase. And the way you measure that phase is a little bit complicated, but basically it works because you have this nonlinear inductor that changes the frequency of the circuit. You measure the frequency, the resonant frequency, and you back out phase, not the phase. Anyway, the point is this gives you a way to measure the rotation. So this is acting as a gyrometer. We call it gyrometer because like a gyroscope, we think of something that's actually physically like spinning and has some angular momentum and has that angular momentum precession. We're calling it a gyrometer because it is measuring rotation, but it's doing it in a different way. Doing it by measuring phase. All right. Okay, this is the most technical slide. So I'm going to try to explain intuitively. You can think of yeah.
Actually, I have a very simple question.
Mhm.
What's little m here?
Little m, yes, sorry. Little m is the mass of a single, helium atom.
Okay.
Yeah.
Single helium atom, and so that's your signal size. And
Yes.
also the size depends on how big that little circle is, basically.
Exactly. So it basically
Okay.
depends on the mass of the helium atom and the rate of rotation and the size of the area enclosed. Yeah.
Okay, awesome. Thank you.
Yeah.
This might be a silly question. Why are you assuming that the phase difference as it comes along is conserved? But that's what it looks exactly again.
So in order for the wave function to be well defined,
Yeah.
the wave function is like e to the I phi.
Yes.
And so you need e to the I phi to have a well-defined value. For example, at this point, at any given point, it has to have well-defined values. And so in that for that to be true, then you need phi to change by multiples of 2 pi.
Okay.
Yeah. Good. All right. So as I said, this is the most technically difficult slide. And it's like really general relativity. So I'm just going to try to explain it as intuitively as I can. The point is that this phase difference that I showed on the previous slide, you can think of it as measuring a time interval. And what is this time interval? Intuitively, you can imagine imagine you're on like a merry-go-round and you have a friend. So you're in a rotating frame, and you and your friend walk around the outside and you try to meet each other halfway around the merry-go-round. So if this is like Galilean physics, you're going to walk around, you're both moving the same speed relative to the merry-go-round, so you're going to meet exactly halfway around. It's going to take you the same amount of time to go halfway around. Now imagine that you have a laser, and you shoot the laser both ways around the merry-go-round. Because we know from this is going to be a little bit of a sketchy intuitive argument, but basically from special relativity, you know that the velocity of the laser beam will be just the speed of light. In the inertial frame, it'll be the speed of light, no matter which way it's going, right? It will not depend on whether it's co-rotating or counter-rotating. And therefore, so that's true in the inertial frame. Therefore, in the rotating frame, the amount of time that it takes for the laser beam to go halfway around in the rotating frame does depend on whether it's going clockwise or counterclockwise around. Okay, this is sort of a sketchy argument because there's no light lasers involved here. But the basic idea is in relativity, there is this time difference, like there's this asymmetry between the time it takes you to go clockwise around the loop and counterclockwise around the loop. And you can think of this time difference as in quantum mechanics, like you know that the phase of the wave function will evolve in time. And so if two paths around the loop take different amounts of time, then they will also accumulate different amounts of phase. And so that is precisely the phase difference that you are measuring in this experiment. So that's that's a long way of saying that by measuring this phase, you are indirectly measuring time dilation. Now, what I just described is special relativity, but it turns out there is also a time dilation due to gravity. And that time dilation is due to the frame dragging effect that I talked about at the beginning of the talk. And so you get 3 phases from this. You get the Sagnac phase, which is the one that comes from special relativity. That just depends on, that's the one I derived on the previous slide. It's just omega, it's the rotation velocity dotted into the area vector. And then you get these 2 gravitational phases, one from the geodetic, one from the frame dragging. You can also write them in exactly the same way as an angular velocity dotted into an area vector. But now the angular velocity is not the angular velocity that you think you have. It's not like the Earth's angular velocity. It is the angular velocity due to gravitational frame dragging. In other words, it is that very, very small angular velocity that you have relative to the distant stars that I showed in the beginning of the talk. And just to make it concrete, this is the expression for the frame for this angular velocity in the frame dragging from the frame dragging effect. So it's not terribly complicated. It depends on things like the mass of the Earth, the radius of the Earth, the helium mass. This is Newton's constant, speed of light, the Earth rotation rate, and your location on Earth is this little r. Yeah?
What are the order of magnitudes of each of these phases, like phase effects?
That's a great question. That's a really good question. Because these ones are really, really, really small. They are 10 orders of magnitude smaller than the effect.
Okay.
And so in practice, this is a big challenge if you want to measure these phases, because you're basically looking for a needle in a haystack, and the haystack is 10 orders of magnitude bigger than the needle. So for context, this Sagnac effect has been measured at Berkeley actually in the 2000s by Richard Packett's group. Unfortunately, he just passed away last year, but he did great work measuring the Earth's. He was the first one to measure the Earth's rotation in one of these devices. And yeah, so we want to measure something that's 10 orders of magnitude smaller than that. And I had sometimes when I give like versions of this talk, I have slides about how you would actually do that. I decided I wouldn't have time today, but the basic idea is these effects depend on different angles. So because you see this omega, this is the Earth's angular velocity. So this dot product will be the same, right? It's here and it's also here. But now you have a different thing. Now you have the position dotted into the area. And you have the position crossed into the Earth's angular velocity. So there's 3 different angles here. You can write all of these expressions in terms of 3 angles. And you can arrange your experiment such that basically this one becomes 0. The question is, can you do that well enough that it really becomes 0 to 1 part in 10 to the 10? That's not completely clear. It's like borderline. Like that is, I think, one of the biggest challenges if you actually want, I hope this experiment will actually get done. And that's going to be like maybe the hardest thing is to actually make this thing go to 0 so you can measure these two. That's a great question.
I guess follow up.
Uh-huh.
Do y'all have an idea of how the calibration procedure would look like? Or is this like do you think it's a hardware limitation or a calibration procedure limitation?
I think it's the way I think about it is a hardware limitation because what you would like to do, I mean, that's one way of solving it at least is to just have such good control over the orientation of your device that you know exactly what its orientation is relative to the distant stars to a factor of 10 to the 10. And for that you need like a really good let's call it tilt meter to tell you what your orientation is. So that's like a hardware thing. Another thing you could do is you could somehow know the Earth's rotation rate to 1 part in 10 to the 10, and you could subtract that afterwards. But then you have to measure the Earth's rotation separately. It's not even constant to 1 part in 10 to the 10. So it's a bit of an open challenge how you like. You could certainly do it if you had good enough you had good enough experiment. But yeah, that's a really big challenge. Okay. The other experimental challenge, so there's 2 challenges. One is the one you just mentioned. The other one is thermal noise. And where does the thermal noise come from? So just for starters, how big is this rotation rate we want to measure? It's 10 to the minus 14 radians per second. That's a really small rotation rate. As I said, that's like 10 to the 10 orders of magnitude smaller than the Earth's rotation rate. What's going to put thermal noise that limits you from measuring this? So if you're at non-zero temperature, as most of us usually are, some fraction of the helium is not in the superfluid state. It's actually in what's called normal fluid state. So it has viscosity. So this beautiful thing where I said you have no viscosity, well, you have some viscosity. And that viscosity leads to dissipation and therefore leads to thermal noise. And people have previously estimated, for example, for helium-3 at half a millikelvin, how well you could measure this based on the thermal noise. The very careful analysis, they found that you would have this thermal noise. It's actually the noise spectral density of 2 times 10 to the minus 13 radians per second per root hertz. What this root hertz means is if you measure for 1 second, you get 2 times 10 to the minus 13 radians per second. If you measure for 100 seconds, you get a factor of 10 better, and so on. So this is kind of, close to this. You could measure for a while, but if you want to measure at the 0.2% level, this requires 120 days of measurement. So that's not great. Another thing I should say, actually, when people have built these experiments before, they're actually not even limited by this yet. They're limited by vibrations in the lab. So if you really want to do this, you go to the people who built LIGO and say, how do I build a really vibrationally stabilized experiment? You could do it. It's like my experimental colleagues tell me not to worry about that part. But just to say, no one has actually even reached this limit yet. But let's say you could get rid of all the vibrations and you're going to be thermal noise limited. Could you do better than this? And the answer of the work I did with my colleagues is yes, you could do better.
Kind of a very simple one.
Yeah.
So why do we use Helium-3.
Okay, yes, this is a good question. The answer is, so people have done it previously with both helium-3 and helium-4. The problem is, the pore size that you need for the junctions has to be on the order of the healing length of the fluid. And helium-4, if you're not close to the lambda point, it has a very, very small pore size. It has like nanometers. And you can't make pores that size with microfabrication. Yeah, with the thought. So in the past, people have done one of two things. They've either used helium-3, where the pore size is the right size, or they've used helium-4, but only like really, really close to the lambda point. And in that case, you're again going to get a high normal fluid fraction for helium-4, and you're going to get the same story. It's going to be bad.
Okay, so
It's easier to hold at 0.5 millikelvin for 120 days than to just like find a way to make smaller points. Like 0.5 millikelvin, that's hard to hold at, right? Like I only know that you can hit those temperatures for like a day before you have to heat up again.
Well, yeah, I mean, no one's doing this for, this is like, I mean, yeah, doing it for 120 days would be unrealistic. People do, I mean, the experiments, they have done these experiments for like a day. You can do it. You can get to 0.5 millikelvin. Because the transition temperature with helium-3 is actually like about a millikelvin.
Yeah, I thought it was pretty close.
Yeah, so you have to be below that even to get the superfluid phase. But yeah, the point is, it would be much better if you could use helium-4.
Actually, sorry,
Yeah.
I have a quick step back. So, the pore size argument makes sense, except is that pore size argument dependent on how far you are from the lambda point?
Yes.
Okay, so it's not just that helium-3 bonds two atoms together, it's also that
Right. So
make it larger.
yeah, it has to do with how far you are from the lambda point. I don't have the exact formula of these slides, but I can show you. Yeah, so as I said, helium-4 close to the lambda point, the pores are the right size. People have done those experiments, but the reason that's no good is because you have, as for helium-3, you have this normal fluid fraction close to the lambda point. So the idea is, what if you could get away from the lambda point where there's less normal fluid? And excuse me. Yeah, so for superfluid helium-4, below about 0.7 Kelvin, the normal fluid fraction basically vanishes, which is to say that the thermal noise is then dominated by different things other than the normal fluid. So far, no one knows how to make a pore size that would work for this. But this is a new thing that is an active area of research in my club. So this paper is in collaboration with Keith Schwab at Caltech. He's working with some chemists to get like chemically I know nothing about chemistry, but somehow chemically fabricate pores that are the right size.
You know the number? Like what size?
It's like nanometers.
No.
Yeah. Apparently this is like, no one's figured out how to do it, but they believe they will be able to do it soon. So that motivates analyzing the thermal noise for such a device. So then you consider other noise processes, something called three phonon processes, and also the mechanical quality factor of the diaphragm. The quality factor is basically telling you, so if you think of like a bell, the quality factor, a high quality factor is telling you that the bell rings for a long time. So the diaphragm is some mechanical oscillator like a bell, and you can measure what its quality factor is, basically how long does it sort of ring. And that turns out to be a really important contributor of thermal noise when you don't have the normal fluid. So again, this is the number we want to measure. We actually want to measure like 0.2% of this, but this is the rate we want to measure. So the big reveal, what we found, the results, is this plot. So on the horizontal axis, you have temperature in Kelvin, and according to my experimental colleague, it would be realistic to work at 10 millikelvin. So that's about here, this line here. And on the left vertical axis, you have the noise spectral density in the rotation rate that you can measure. So this radians per second per root hertz. So 10 to the minus 13 right here, this line is what was estimated for helium-3 or for high temperature, like this analysis previously with helium-3 was at this line. So you can see and hear what these different colors are. They're different quality factors of the diaphragm. So for example, this purple is a very, very high quality factor, 10 to the 9. And then you get blue is 10 to the 8, 10 to the 7, 10 to the 6, 10 to the 9, 10 to the 4. And so this solid line is telling you from all sources of thermal noise, we considered three things. We considered the three-photon process, the mechanical quality factor of diaphragm, and we also considered something called the thermal viscous effect. Taking those three into account, you get these solid lines, which have this interesting shape. I'll ask them to it up here. The dashed line is what you would get if you're only considering the quality factor of the diaphragm. So what this is showing you is at high temperature, you're being limited by this three-photon process and the thermal viscous effect. Those two effects are limiting you, whereas the diaphragm quality factor is not limiting you because the actual thing is way above the dotted line. But down at low temperature, these asymptote towards the dotted line, and that's telling you at low temperature, you're just going to be limited by the quality factor of the diaphragm. And so if you can make a better diaphragm, you can make a better rotation sensor. So what's realistic? Quality factors of 10 to the 5 already exist. So that's very realistic. You could keep pushing it. And according to Keith, my experimental colleague, if you used the best materials that have been like demonstrated in any system, you should be able to get a quality factor of 10 to the 9. So this is like best, like you'd have to work for this. This is not at all trivial. This is non-trivial. Like 10 to the 5, easy. 10 to the 9, very difficult. But like experimentalist tells me this might be realistic. And let's look at what you would need. So this 10 to the minus 14 number, that is the size of the frame dragging effect. And remember, these numbers are basically, you can think of them, this is what you would get if you did a 1 second measurement. So if you measured for 100 seconds or 1,000 seconds, that's all realistic. You could do better than this. So let's say you took a quality factor of 10 to the 5. And let's say you measured for like 10,000 seconds. So that would bump you down another 2 orders of magnitude to here to here. So you would be in the range where you could think about measuring frame dragging at the 0.2% level. And just to make an explicit expression, I guess this is my last slide, good timing. Just to make that very quantitative, I have said here, if you assume the best material, so this is the 10 to the 9, you could do this 0.2% measurement in 35 minutes. And if you assume a less good material, you could do it. Is that right? I forget if this might actually not even be the best material. I have to double check which number this is for. But the basic conclusion is on a time scale of, hours, like within a day, if you tried hard enough, it seems like you could measure frame dragging at the 0.2% level, which is exciting. So yeah, then just to go through the conclusions, these superfluid geometries are extraordinary sensitive rotation. And you could get a sort of breakthrough by using helium-4 at millikelvin temperatures using these new junctions, which has never been done before. That would give you very low thermal noise, but that would give you this possibility of measuring frame dragging at the 0.2% level. Of course, this is assuming you've done a lot of other things. You've vibrationally isolated. You've figured out how to distinguish this from the Sonic effect, which we talked about. It's a real challenge. But if you could do this, you can then put new bounds on post-included parameters. Actually, I have to be careful with this statement because the best bounds currently do not come from frame dragging measurements. They come from like other solar system measurements. So whether or not they would be the best bound, even though we would definitely claim that we measure frame dragging the best, I'm not sure if that would be the best, if that would really push in parameters. I think it might push one of them, but not the other. If you could do that, you could test general relativity against other metric theories of gravity. And now the final thing, which is crazy number that no one's going to believe. I told you that this is connected to a time measurement, the time difference between light going clockwise and counterclockwise around the ring, basically. And just another cool interpretation of this time, if you're in a rotating reference frame and you try to like synchronize clocks. Has anyone here taken special relativity? Some people? Okay. So in special relativity, you learn about like synchronizing clocks. You send a laser pulse, it bounces back, you click start on your clock so that it matches someone else's clock. It turns out it is impossible to synchronize clocks in a rotating reference frame. If you try to synchronize with your neighbor and your neighbor synchronized with his neighbor and her synchronized with her neighbor, and you go around the ring, the last person will disagree with the first person about the synchronization. It's impossible. So that's another interpretation of what this time means. This time that you're sort of indirectly measuring here is 10 to the minus 35 seconds. You can actually even do a little better if you measured for a little longer. But let's say 10 to the minus 35 seconds. This is 20 orders of magnitude better than the best atomic clocks. Now, caveat, it's not measuring the same thing. Like, it's not useful in the same way. So I don't want to make any atomic clock people upset. But it is remarkable that it seems like you're somehow indirectly measuring a time interval that's that much smaller than the best atomic clock. And it's also only 9 orders of magnitude larger than the Planck time. The Planck time is a unit of time. It's 10 to the minus 44 seconds. And this is a time when people think maybe some quantum gravity effect will happen. Maybe time will be, I don't know, quantized in intervals of the Planck time or something. It's a little bit sketchy, the things people say about it. But it is an important, very, very short, it's an important time if you care about quantum mechanics and gravity. And this is like a lot closer to the Planck time than anyone could dream of getting with conventional atomic clocks. So yeah, we're now thinking about what physics could you do with this kind of measurement. And I'm also thinking about what other gravity effects could you measure, like there's been some proposals to measure gravitational waves with this kind of device. So yeah, I'm interested in further applications of this extreme rotational sensitivity. And with that, thank you for listening, and thank you to my collaborators and funding agency. Thank you.
Thank you so much, and thank you so much for staying very engaged in this conversation. So I think we still have time for questions.
So you said you have a brief photon model?
Mm-hmm.
What is that?
This is basically a process where a single phonon scatters into two phonons. It like decays into two phonons. It's apparently a process that happens in helium.
So this is like really, really low energy phonons, or is it so? Because there are ways like, okay, actually, I guess a better question is, in your model, like of this noise source, where does the energy of the phonons go? Does it eventually decay into the wall, or does it just bounce around and then kind of screw everything up? Or decay into like low enough energy phonons that you no longer think about it.
Yeah, so it's the way we think about it is so you think of it at these very low temperatures as like a ballistic gas of phonons.
Yep.
Yeah. Does that answer the question?
Yeah, I think so. That means that I guess the only way to suppress them would be to just get cold enough, like low enough that you never have any source of them.
Right.
And the
right.
assumption, is there like an assumption that the source of it is like a particle impact or something? Because
I think these are thermal phonons. Just like, yeah.
thermal phonons,
Like there's gonna be some thermal spectrum of phonons.
yeah. I'm used-
Basically, black body.
Yeah, I'm used to thinking of these at such low energies that you don't think about them, but
I
this
see.
experiment forces you to think about them.
Yeah,
Um,
I'm by no means an expert on the like Keith of the experimentals. He is a wizard with this, and I'm just learning. But this is my understanding: is that you can model it as a thermal gas of phonons at this temperature. Yeah, I think it.
If you're in the rotating reference frame and you sync with your neighbors,
Mhm.
why would the first person agree and disagree with the last person in the time clock?
Yeah, it's a little bit tricky to see. One way to think of it is what's the best way of explaining it? So are you familiar with special relativity at all? So basically if you in special relativity the like you may have heard like like the relativity of simultaneity. So like whether something's simultaneous in one frame,
Oh, yeah.
it depends on your frame. So you can, so let's say you have a train moving at some speed v, and you synchronize the clocks on the train. And now you look at the train. Let's say the clocks are on the windows of the train, and I'm standing outside the train. I'm looking at the clocks. To me, looking from outside, the clocks are not going to be synchronized. The one at the front of the train is going to be different from the one at the end of the train. And now you think the way you think about this is you wrap the train around in a circle on itself. Right? This is a rotating reference frame with a train wrapped in a circle. And this basically this this clock at the front of the train and the back of the train, to me, outside the train, they don't agree. And when you wrap it in a circle, like that causes a problem, right? You have to have a unique value. Yeah?
Yeah, thank you for the talk. It's very interesting and I'm very clear about this experiment. So are your experiments ground-based or you send them to space?
Part of the pitch that we have is that this could be done on the ground, because this measurement has not been done on the Earth before. The challenge of doing it on the Earth is you have a lot of vibrations that you need to deal with. So, of course, the challenge of doing it in space is you're in space. So, yes, I think the claim is that you could talk to the LIGO people and find out how to do really good vibration isolation. Maybe you'd put it in some like abandoned mine shaft in a seismically quiet area. And you should be able to do it on Earth, yeah.
Yeah, but I have another question. So apart from the noise from the vibration, it seems to me you need to also take into account the fact that there are masses moving around in the lab. Because you said that the signal to the noise ratio, the signal to the other effect, the ratio is about 10 to the minus 10.
Right. Yeah, that's a good question. So there would potentially, so this device is not sensitive to static Newtonian sources. So it doesn't it will be sensitive to time variations in that, but that's going to be a time dependent signal, whereas the thing you're looking for is a static signal. So it is a challenge, you're right. It's something you have to think about, but I think it's not going to fundamentally mess it up. But that's a good question. That requires more thought. But I think basically the fact that the only contribution there is the time varying part, you can probably like average it out or filter it out or something. Filter it out of your signal.
But it has different characteristics with the time dependence caused by the rotation, right?
Yeah, so the rotation itself is approximately constant. And so it's just going to cause So, okay, the way this actually works is very complicated because I showed you, yeah, the way I'm talking about this is a little bit oversimplified. As I said, there's this like sinusoidal current across the thing. And what's actually going to be happening here is you're going to drive this. It's going to have some time dependent part and some DC part. And the thing you actually want to measure is the DC part. And that DC part should not have any contributions from like time varying exponential external Newtonian forces, as long as they're like not like super low frequency. I don't know. It's worth thinking about, but I think what you actually are measuring here is a DC phase, and so it's only going to have that DC part. Yeah.
Thank you for the talk. I also had a question about the construction of the Josephson junction. About that. On the level of, so you mentioned there's like a membrane, right? For the helium group. What is this membrane composed of? Like you mentioned, I'm assuming it's not actual like nanoscale holes in junction, right?
So the current existing ones you make like lithographically. So I don't actually know what the materials are, again, because have never done this and that is purpose. But however you do some kind of lithography and you actually do make micrometer sized holes in some material.
Okay.
The way that we would build the new junctions would be like some kind of chemical structure which has nanometer size.
Okay.
I
Yeah.
have a very long question.
Uh-huh.
I think we can talk about.
Okay.
It's
That's good.
super interesting. Thanks for the.
Yeah, thank you. Great questions from everyone.
Thank you so much, everyone, and please thank always. If you have more questions, feel free to stay for a little bit. And yeah, thank you so much. And before you leave, if you have
Thanks for coming.